All right, so as we look at section 9.2, we're going to actually do the physical significance test for a population proportion. Whereas on 9.1, we kind of went through the characteristics of stuff, went through what was a type 1, type 2 error. Again, I highly recommend watching those additional videos I posted on Google Classroom on the explanation of a type 1 and type 2 error. They do a heck of a lot better job than I do on explaining it, so I think it's a great resource to use. Again, and I've been shooting messages to you all, about AP exam stuff. So we'll talk about that here in a little bit too. So as we look at doing our significance test, as we actually do the test today, and before we do the test, we need to make sure we meet conditions. So one, is it random? Does the data, does it come from a well-designed, simple random sample or a randomized experiment? If it doesn't, then we don't do it. We can't infer to the population and establish some type of cause and effect if we don't have that take place. Next condition is the normal part. Sampling distributions of the statistic is approximately normal. Our normal condition, again, is still, since we're dealing with proportions, the n times p, is it greater than equal to 10, or is n times 1 minus p greater than or equal to 10? And then, and again, we're going to replace the p with p naught, p sub 0. Okay, so now where does that p sub 0 come from? That's the same p, same percentage that we use in the null hypothesis. So whatever proportion percentage is that we're comparing it to for the population in the null hypothesis, that's the one we use for this NP greater than or equal to 10 and so forth. We do not use p hat in this part here for the hypothesis testing. So you need to make a note. Do not use p hat on this one, as you're testing the normal condition. For independence, same thing. Is our sample size times 10, is it less than or equal to the population? If we're bigger than the population, then we can't do it. We don't have independence. When we look at our calculations for our test statistic and p-value, our test statistic is going to be known as a z-stat. Okay, so our test statistic in this case is a z-stat. This is what I usually have people write down. Instead of writing z-score, we write down z-stat or a z-statistic. Is what we write down when we show our work. So a significance test, you use sample data to measure the strength of the evidence against the null hypothesis, HO. Here are some principles that apply to most tests. One, the test compares a statistic calculated from sample data with a value of a parameter stated by the null hypothesis. Values of the statistics far from the null hypothesis in the direction specified by the alternative hypothesis give evidence against the null hypothesis. To assess how far the statistic is from the parameter, we use our standardized z-score. We standardize our by doing this, our standardized z-score of the statistic. So the value of this thing is called our test statistic. Again, I'm going to have you guys refer to it as your z-stat as you show your work, your z-statistic. And the reason why we want to say z-statistic when we come back from spring break and we start doing all this stuff for means where they give us, and we're comparing it to mu, we're going to have to do what's called a test statistic, but it's actually a t-value. It's a t statistic. So we're going to specify here the z-statistic. Again, how do you come up with it? It is basically your statistic minus the parameter divided by the standard deviation of the statistic. So what does that mean on the formula on the sheet? Our z-stat, our z-statistic is equal to p hat minus p sub 0, so p naught, over, there's our standard error, the square root of p naught times 1 minus p naught over n. That's how we calculate our z-statistic. We take our p hat value, subtract the null hypothesis value from it, and then we divide it by the standard error, which is the square root of the null hypothesis value, times 1 minus that value divided by the sample size. Now, where we got to be careful on is we got to be extra careful on the multiple choice type of questions, because they're going to stick the p hat value in there in the bottom. And what you got to remember is when I'm doing a hypothesis test, I am only using the p hat once, very top left hand side before the minus sign. I'm using the p naught value 3 times, or 2 times, and then 1 minus it on the 3rd time. So that's where you got to be careful as we look at ruling out answer choices. The test statistics measures how far away the sample result is from the null parameter, and in what direction of the standardized on a standardized scale. You can use the test statistic to find the p-value of the test. And what is the p-value? What does the p-value mean? It's the probability of getting the result by chance. Because remember, we have to do some interpretations here. So what is the interpretation of the p-value? It's the probability of getting that result by chance. As we talked about before, they're not going to tell you to use the 4-step process to do the significance test. You need to come out and go ahead and do it. So in our first stage, we're going to state what the hypotheses do, that do we want to test and at what significance level. So here's an example. We're going to test a hypothesis that the true proportion, fill in what our proportion is at a something significance level. We write a little statement. We have to put down these statements here as well, the ho and the ha statements. We got to put those down there. Our null hypothesis will always have an equal to sign. We do not have it be one of the inequalities in the null hypothesis. Our alternative hypothesis will always have one of those 3 inequality symbols. It just depends on, are we doing greater than, are we doing less than, is there a difference? Okay. And then we have to explain what P represents in context of the problem. We have to define this. So when you look at just the statement phase of a problem, in a way, this is like a 4-point part right here. You get 1 point for this first part. You get 2 points for getting this part set up right. And then you have to show what is P. You have to define what P is. So to get full credit for this first part, you have to hit all 4 of that stuff. Okay? You miss any one of those 4 things, and it's that out of 4. Minimum you should be getting is at least a 2 out of 4. Minimum is at least getting these things. Now, we don't always want to do the minimum, but at least having that part there gives you at least 2 out of 4. But we also want to make sure we define what P is, and we make the statement of what we're trying to do. In our plan stage, we're going to do a 1 sample Z test for proportions. Remember, last chapter was a 1 sample Z interval for proportions. Now it's a Z test. We make sure we go through the conditions here. And I'm sorry about the big fonts there. Again, that should be an NP and a little 0. Should be NP and then a little 0 like not. I forgot to hit the subscript on those. So that's not NP times 0. It's NP naught. Okay, so I meant to go back and change my Word doc and I didn't. So if you want to rewrite those off to the sides the way they're supposed to look like. And again, this is what I thought was the hardest thing in this course. When we start using the P, we use P hat. Now we're using P naught in this stage right here. So it gets confusing sometimes. Independence still stays the same thing. 10% rule. Is 10 times little n less than or equal to big N? In the do stage, we're actually going to compute what the P hat is. We're going to go through and compute what that is because we need that for the first part of the fraction. When we do this by hand and we set up the by hand formula, like on a multiple choice, we have to have the P hat value there. And usually as a decimal is what they have it in there. They don't have it as a fraction. So usually you'll go ahead and convert it to a decimal is what they have there. Again, as we compute the test statistic, we go through and we use that formula to compute it. That is, I believe that most of that is on your, in some form or fashion on that cheat sheet guide that we get to use for the state test. How do we find the p-value? When you're doing it by hand, we do a normal CDF with the lower bound, which happens to be, and then an upper bound. And again, that's all those two things are dictated off of, are you doing a greater than or less than, is what you're doing here. And typically your Z statistic is what's being put in for those lowers and upper bounds. It just depends on, are we doing less than that or greater than that? And again, since we're doing a normal CDF and we standardized it because it's a Z, our mean is 0 and our standard deviation is 1. If the I put a little couple statements here. If the alternative hypothesis is greater than the lower bound in a test statistic, then our upper bound is 10. If our alternative hypothesis is less than the lower bound, then the lower bound is negative 10. So if we're using a greater than statement, then we can have our upper bound be, be 10 and so forth. So, and then we keep in mind when we're doing a not equal to, we got to make sure we multiply by 2 for the normal CDF. And then we have our conclusions. We interpret the value as following. We say since, and then we say what our p-value is. Since 0.0015 is less than or greater than whatever alpha it is, we fail to reject. So if your p-value is greater than your alpha, we fail to reject the null hypothesis. We do not have significant evidence. If the p-value is less than our alpha, then we reject the null hypothesis. We have sufficient evidence for what's taking place. Again, we got a little bit more notes than we actually get to practice it and see it in context, which hopefully will make a little bit more sense. So what happens when the data don't support the alternative hypothesis? There is no need to continue with the significance test. So that's basically meaning, like, if we take our p-hat and the p-hat is nowhere close to what we're trying to do, then there's no need to continue the significance test. The conclusion is clear. We failed to reject the null hypothesis. So if we have, like, for example, a p-hat that came out to be like, 20%, and we're thinking that it's that the actual amount is greater than 50. Well, in our one sample is 20% greater than 50? No, so there's no point to go ahead and do the test because we're not going to have any evidence for it. So that's what that's kind of saying there, is we compute that p-hat because sometimes we can stop with the way the p-hat works out and say, you know what, that's not even going to be close to what we think it is. It's not in that range of where we're thinking, so don't bother, because again, if we did, we're just wasting our time. We did a test and we end up finding out that, hey, we didn't have the evidence. If you aren't paying attention, you may end up performing a test when you don't need to and get the same conclusion. So you do a lot of work for nothing. So let's actually just start doing a test. This is where hopefully it'll start making a little bit of sense, putting everything that we did last Friday in the lesson, which was a lot, and then we kind of go from there. So on shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate this, a random sample of 600 American Idol fans is selected, and they are shown the audition tapes of 12 never-before-seen contestants. For each fan, the order of 1 through 12 of the 12 videos is randomly determined. Thus, if the order of performance doesn't matter, we would expect approximately 1/12 of the fans to prefer the last contestants they view. In the study, 59 out of 600 fans preferred the last contestant they viewed. Does this data provide evidence that there is an advantage to going last? Okay. So as we start the process, in our statement phase, we're going to test the hypothesis that the true proportion of American Idol fans that prefer The Masked Singer. Now, we're going to prefer that The Masked Singer is 1/12. Is that what the true proportion is? At a significance level, do they tell me? They don't tell me a significance level. So we said last week in our notes, what do we use if they don't specify? Anybody remember? If they don't specify, yeah, we do. Well, 95 is the confidence interval. We use a 5% for an alpha. Okay, we use a 5%. There's three choices: 1%, 5%, 10%. If they don't specify an alpha, it's 5%. Is what we use. That way, we compare our p-value to 5% because that's what the court of law does. Okay. And then, Michael, did you talk to Dr. McDowd on Friday? He hadn't said anything yet? Okay, I'll try to find him today. Because I can add you to this notebook here. And that way you can see all the stuff. So what is our null hypothesis? Our P0 is 1/12. All right, our P0 is 1/12. Now, I'm going to go ahead and convert that to a decimal. 0.0833 repeating. I mainly had that for when we set up the test statistic. Is that way we have that decimal is why I converted it. They think that it is greater. Okay, again, they think that it is greater than 1/12. So our alternative hypothesis P0 is greater than 1/12. And then now we would finish up the rest of the state phase where we got to define what P is, where P is the true proportion of American Idol fans that prefer the last performer. The Masked Singer. All right, now, if the conditions are met, we will perform a what? A whoops, sorry, I forgot the NE in one. One sample Z-test for proportions. All right, random. They told us random sample of 600 fans. Random sample of 600 American Idol fans. Normal. All right, so I remember I'm doing my sample size, 600, times my P0. So that's 1/12. Is that greater than or equal to 10? Well, that happens to be 50, which is greater than or equal to 10. Then I have to do the 600 times the 11/12. Is that greater than or equal to 10? Well, that becomes 550, and that's greater than or equal to 10. So we are normal. For independence, 600 times 10 is 6,000. Reasonable to assume more than 6,000 American Idol fans. Because if there weren't, would that show still be on the air? Nope. All right, so we met all three conditions, so we can go ahead and calculate it. Okay, we can go ahead and calculate it. Now, what is our P hat? Our P hat was 59 out of 600. And 59 out of 600 works out to be 0.0983. Now, is that greater than our null hypothesis at the moment? Yeah. So I do have some evidence in my sample that it is actually greater than 112. All right. So that lets me know that, hey, let's go ahead and keep doing our process. If that 59 out of 600 was less than 0.0833, we would stop and say, hey, listen, we would fail to reject. Okay. We don't have the convincing stuff. So now we get to find our z statistic. So our z stat is equal to 0.0983 minus the null, so 0.0833, over the square root of 0.0833. 1 minus 0.0833 is 0.9167, all divided by 600. Again, that we need to make sure we show those as I pick problems in the AP test. They have somewhere it says, hey, what's the correct test statistic setup? So we want to make sure we write that down there. And then now we would compute it. Doing a little brief simplifying, it becomes 0.0015 on top divided by 0.01128 on the bottom, which comes out to a z-stat of 1.3298. Now, I am doing a greater than. So with that in mind, as I set up my normal distribution, my normal CDF, my lower bound is my z statistic. So 1.3298. My upper bound. Again, we can use some really big number. Since we're doing z-scores, 10 is fine to cap it at, since we're doing z-scores. We can do I always have you guys put 1 million. But again, since we're doing z-scores, we can go ahead and cap it at 10 if we want. If you just want to get in the habit of keep writing the big number, you can do that too. Again, it is standardized, so our mean is 0 and our standard deviation is 1. That's the whole reason why we're using the normal CDF in this topic, is because we have a standardized z value. And then now let's grab the calculator and let's see what the calculator says. All right, so smaller screen, second vars, normal CDF, 1.3298, 1.3298, upper bound. Again, you can do something big, leave the rest alone, 0 and 1. Hit enter a few times, and this tells me that it's approximately 0.0918. Now, as we look at writing this up, again, this little conclusion pre-filled will look a little wonky, but we have to compare 0.0918 to our alpha value, which was 0.05. Is 0.0918, is it less than or greater than 0.05? It is technically greater than, correct? So since the p-value is greater than our alpha, which was 0.05, we failed to reject. And then they actually have the words, the null hypothesis. The null hypothesis, there is not convincing evidence to conclude that there is an advantage to performing last in American Idol. Now, at times, I know that's just one example, but at times they may ask a second part, like a subpart question here, and say, hey, would your decision change if we did an alpha of 10%? Or would we keep the same conclusion? If I was comparing that to a 10% alpha, do we still fail to reject? Or do we reject? Is 9% greater than 10%? No, so we would actually change our decision. We would say we reject the null hypothesis. There is convincing evidence to support that claim. Yes, ma'am. That's why we take it out all the way to, we keep those extra decimals. That's why. So it's a good question. That's a great question. That's why we take it out, and we take it out, 4 or 5 decimals at least, and then we compare it. And then, that way, because very rarely will it end up being to where it rounds up to be exactly equal and stuff. So, but yeah, so, I mean, it could happen. Never saying it's never going to happen, but it could happen. I have not experienced it yet in any of doing these where that actually works out that way. All right. So now, as we get to practice a little bit more, eventually we get to go through and write the statements and stuff. But we get to tie it in with a confidence interval too. So, again, you're more than welcome to work ahead of me, or if you just want to work with me, you can. According to the National Campaign to Prevent Teen and Unplanned Pregnancies, 20% of teens aged 13 and 19 say that they have electronically sent or posted sexual suggestive images of themselves. The counselor at a large high school worries that actual figure might be higher at her high school. To figure out, she gives an anonymous survey to a random sample of 250 of the students, 2,800 students in the school. All 250 responded, and 63 admitted to sending or posting sexual images. Carry out a significance test at an alpha of 0.05 level. What conclusions should the counselor draw? So typically, this is all we see on a free response question. That's all we see it as. We just see that, boom, and they ask you to go ahead and carry out a significance test. So this is where, again, I would recommend you writing down the 4 words: state, plan, do, conclude, give some room. And then in the statement phase, we would go through and say, okay, what do we want to do? We want to test the hypothesis that the true proportion of teens aged 13 to 19 that have electronically sent or posted sexually suggestive images of themselves is 20%. Again, here is where they brought this very first part here. This is where they took out and created the null hypothesis out of that part right there. All that right there was the H sub O. We're going to test that if that's the true proportion. Our null hypothesis is that P is equal to 0.2. Again, you can say P naught. It's okay. You won't get marked off if you say P naught is equal to 0.2. That's fine. If that reminds you to make sure you use the P naught later on in the formula. Here, she thinks it's greater than. Okay, she uses this thing that it might be higher. So that lets us know that we're doing greater than 0.2. And then she goes through and defines what P is. P is the proportion of students sexting or sending sexually suggestive images. We're going to perform a one-sided z-test for proportions if conditions are met. So random. They tell us in there they did a random sample of 250. So let's change colors. Random sample of 250. Normal. All right, so here we go. Now we're going to shorten this up a little bit. 63 admitted. So 63 is greater than or equal to 10. And then when we look at, okay, what's 250 minus 63? Isn't that like 187? 187 is greater than or equal to 10. Okay. So I just kind of went through that a little bit quicker. Just took the 63, and that's greater than or equal to 10. And then what is 250 minus 63? Again, that's that one. 250 minus 63 gave me my 187. Independent. All right, let's see. 10 times 250, which is 2,500. That is less than the 2,800 in the school. So our independence is met. Again, notice I didn't say it's reasonable to assume. They told me that there was more than 2,800 students in the school. So I can say, hey, listen, we're less than that. Now we're ready to do the do phase. So let's calculate our p hat. So what is p hat? So p hat, not p value, p hat. P hat is equal to 63 out of 250. As a decimal, that works out to be 0.252. 0.252. So as I set up my formula, our z-stat is 0.252 minus the null piece, which is 0.2, over the square root for the standard error here, the standard deviation, would be 0.2 times 0.8 over 250. So on top, it's 0.052 divided by the bottom, which is 0.0252, 9872. Now again, I went ahead and worked that out in advance. What is my z-stat? It is 2.05548. Now, what's my p-value? I'm going to get that by doing a normal CDF. My lower bound. Again, we're doing greater than on this one, so that means my z-statistic is my lower bound. If you're doing a less than, then your z-statistic is your upper bound. My upper bound, again, I can use 10, I can use 1,000, it doesn't matter. My upper bound is some big number. My mean is 0. My standard deviation is 1. And then we go to the calculator. And then type in what I have here. Let's see. So with that in mind, 2.05548. Leave that alone. Leave those alone. Enter through, and I get 0.0199. All right. Now we can now we compare. And I would get in a habit of showing, like on there, now I would compare it to 0.05. We are technically less than 0.05. So since our p-value is less than our alpha of 0.05, we reject the null hypothesis. There is convincing evidence to conclude that more than 20% of teens at the school has sent sexually explicit photos of themselves. Do a little pause, let you catch up. How many cups a day are you supposed to drink of water? What do they recommend? Is it 8 cups a day? I thought it was 8 or 6. 8 or 6. So 8 times 8 is 64. All right. I'm almost on the 60s right now. That's pretty good. Get all my water in before lunchtime. Any questions so far? Again, it will speed up or easier. Remember, we always show the normal CDF. I'm going to show you in the calculator on the next one how we don't have to use the normal CDF. Yes, Mackenzie?
So the...
You would... Oh, you're right, I did move you on that one, didn't I? And we should be doing the point two. We should be doing the point two and the point eight. Right, we shouldn't be doing the
I just
P
wanted to make sure that-
You know, you're right.
I looked ahead and I was like, wait a minute,
Yeah,
there's something wrong.
yeah, no, we should be. No,
I was so confused.
my apologies. No, no, you're right. I mean, we get so used to all those other ones of using the sample.
Yeah.
Yeah, no, that was my bad on that one.
I was like, I know we,
Yeah, no. That's how easy it is to make that mistake. So we should be doing 250 times 0.2. And if I looked at my notes, I'd see I did it that way too. 250 times 0.8. My bad. So again, that would be what, 50 and what's the other one?
200.
There'd be what?
200.
200? Okay, so it'd be 50 for this one, and that one would be 200. Yeah, no, my bad. I'm sorry about that. I really botched that sucker. All right, let's get rid of that evidence. All right. Two-sided. When we do a two-sided test, we're looking for convincing evidence that the true parameter is different from the hypothesis value. So our alternative hypothesis, we use the not equal to symbol, is what we use for a two-sided test. I'm going to do this one after we get through the stage here for the do stage. I'm going to show you how to do it on the calculator, how to do it a little bit faster, okay, without using the normal CDF. According to the Centers for Disease Control and Prevention website, 50% of high school students have never smoked a cigarette. Taya wonders whether the national result holds true for her large urban high school. For her statistics class, Taya takes a simple random sample of 150 students from the school. She gets responses from all 150 students, and 90 say that they have never smoked a cigarette. What should Tanya conclude? Give appropriate evidence to support your answer. All right, so here we go. In the statement phase, we're going to test the hypothesis that the true proportion of students who never smoked a cigarette is 50%. At A, did they specify? No. So 0.05 significance level. Sorry, the green's great on just the video. It's not great on the projector screen. All right. So what is our null hypothesis? P is equal to 0.5. What's our alternative? Tanya wonders whether this national result would hold true. Okay, do they specify if it's greater than or less than? No. So we would do A not equal to. Where P is the true proportion of students. Technically, we should say at her high school, but who never smoked a cigarette. Again, I'd probably specify here that at her high school, the true proportion of students at Taya's high school who never smoked a cigarette is what I would probably put in there for the statements, because it isn't just in general. It's just she's testing her school. What'd you say?
Like the one at the top.
Yeah, and I would do that one too. The students at Taya's high school. I would put that in both places. If conditions were met, we will perform a one sample z-test for proportions. Here's where you got to make sure that you're careful on, don't use the code in the calculator. I'm getting ready to say for that part here. You want to go ahead and say that, we're doing a one sample, z-test for proportion. not the abbreviated code that's in the calculator. All right, random. They said simple random sample, SRS, of 150 students. Normal, 150 times 0.5 is 0.75. Oh, sorry, not 0.75. It's just 75. My bad. Is 75. That's greater than or equal to 10. 150 times 0.5 is greater than or equal to 10, because that's also 75. So we meet the normal condition. Independent. 10 times 150 is 1,500. Now, did they tell us how big the high school was? No. However, they do say large urban high school. Okay, so reasonable to assume more than 1,500 students in a large urban high school. Again, we're an urban high school. We have how many students? Right around that mark. We're 1,450. We teeter on the 1,500. You go to Gallatin High School. They're just 12 miles down the road. They're a large urban high school. They got close to 2,000 kids in the high school. Okay. If we want to get closer to Nashville, and we start going through your McGavick's and your Hunter's Lane and your Overtons and some of the other ones, those are over 2,000. Okay, so it's 100. So we meet that independence clause since we're right on that border for us for being urban. You start going further out to your Portlands, your Westmorelands. Now you're becoming more rural. Mount Juliet, Lebanon, they're not rural, they're urban. You'd have to go out past Mount Lebanon in order to get to rural, is what you'd end up having to go to, just to give you geographic things. So with this in mind, I'm going to show you the calculator version. Any questions so far? All right, so in the calculator, we're going to do a one prop z-test. That's what we're going to do in the TI-84. So as I go get my calculator back up and I clear my screen, I'm going to go in here and say, all right, stat over to test. And as I go through, it is actually option number 6. Option number 5. 2 prop is tomorrow. 1 prop z-test. That's a 1 sample z-test for proportions is what that's saying. So I'm going to press enter. I get to put in what my null hypothesis is, 0.5. Now, she said that it was 90 out of 150. All right, so our p-hat was 90 out of 150. So that means my x is 90, my n is 150, and then now we got to pick which one of those proportions am I dealing? Am I not equal to the null hypothesis? Yes, we're saying in our alternative hypothesis, we use the not equal to symbol. So we want to use that symbol. And then we're going to go down to calculate and hit enter. And that tells me that as I went in there and I put down, let's see, my P naught was 0.5. My X was equal to 90. My N was equal to 150. And I did not equal to P naught. And then that gave me a Z statistic of 2.449489,743. So that's the answer to that fraction when you did the subtraction and divided by the square root of the standard error. That's what that answer was. And then what is my p-value? My p-value was 0.014305. I don't need my p-hat, but they gave it to me. Okay. So now we get to look at it and we get to make a decision. And we compare. Get my thing back here. It always, whenever I zoom back out like that, it always messes it up. I compare that to 0.05. 0.014 is less than 0.05. So since the p-value is less than 0.05, we reject the null hypothesis. There is convincing evidence to conclude that the true proportion of high school students at Tyus High School who never smoked a cigarette is different from 0.5. Now, do we know which way? No, we just know it's different. Could be less than, it could be greater than. Okay? Technically, what do we have? 90 divided by 150 was what again? I think it said our p-hat was 0.6. We didn't write it down, but it said it on the calculator. So is 0.6 bigger than 50%? Is 60% bigger than 50%? Yeah. So we did have some evidence. That's why we kept on going through it. All right? The p-hat value alone let us know that, hey, we got some evidence that, it is different than 50%. Is what it's saying. So, again, most of the time, we don't have those pre-filled in. So usually the script on the interpretation is, since our p-value is less than or greater than our alpha, whatever the alpha is, we reject or fail to reject the null hypothesis. In our lesson on Friday, we talked about those are our only two options, is to reject the null hypothesis or fail to reject. We don't have an option of accepting anything. So anytime you see on a multiple choice we accept, we don't choose those answers. We steer away from those. Confidence intervals and significance testing. They are related. A significance test can tell us if the smaller specific population proportion differs from the entire population proportion. Confidence intervals give us an idea of what the actual proportion may be. Therefore, a confidence interval can be more informative. So what we're going to do here is we're going to do a one sample Z interval for proportions is what we're going to do. And we already know what the hypothesis test is that it came out to be. Now we're going to do a confidence interval from there. Okay? All right, so Taya found that 90 of the 150 students said they had never smoked cigarettes. We checked the conditions for performing a significance test earlier before we construct a confidence interval. For the population proportion P, we should check that both N times P naught are greater than or equal to 60 or greater than or equal to 10. Since the number suggests success and the number of failures in the sample is 90 and 60, we can proceed with our calculation. And then they asked us to calculate a 95% confidence interval for the true proportion of students at the school that have never smoked a cigarette. So in our statement phase, we estimate the true proportion of students at the high school that have never smoked a cigarette with 95% confidence. Our plan is to use a one sample Z interval for proportions. Again, if they specify in the problem that conditions were met or assume the conditions were met, we just state that in the plan stage after we state what we're doing. So if they tell you that, hey, assume the conditions were met, we can just say that, conditions were met. All right, we did it in the significance test above. That's why we don't have to do it again. So what is our Z star? So our Z star, we got to do an inverse norm. Our area is 0.025. Our mean is 0. Our standard deviation is 1, which gives us about a 1.96. I mean, we know on the calculator inverse norm it's 1.9599, blah, blah, blah. But again, if we went to the Z table, that's what we'd be using. Again, now, what is our, I'm just going to do the interval by hand. So our P hat was 0.6. All right, P hat was 90 out of 150, which is 0.6. Plus or minus 1.96 times the standard deviation of 0.6 times 0.4. What'd you say, sweetheart?
I just couldn't see what the mean. I didn't know what the area was.
0.025. All right, so 0.6 times 0.4 over 150. Again, we're going back to using, in this case, we're using the P hat. Again, the confidence interval, we're using the P hat in there. Hypothesis testing, we're using the null P. That's why it gets so confusing. All right, this works out to be 0.6 plus or minus 0.0784, which gives us the following interval. 0.5216. Sorry, that 2 and the 5 merged together. To 0.6784. There's our confidence interval. And then as we go to write up our statement here, we are 95% confident that the interval from 0.5216 to 0.6784 captures the true proportion of high school students that have never smoked a cigarette. At Taya School. And that's why I tied in that Taya School earlier and stuff, because that only applies to her school because that's where the sample was based off of. We can't make an inference about all high school students in the United States because our sample was just from that one school. We'd have to get a random sample from the whole United States to be able to infer about the whole United States if that 50% was accurate in the process. Now, here are some connections between, as we get ready to wrap up, connections between confidence intervals and two-sided tests. There is a link between confidence intervals and two-sided significant tests. The confidence interval gives an approximate range of values for P naught that would not be rejected by a two-sided test at the 1 minus confidence significance level. However, with proportions, the link is not perfect. It's an approximation because the standard error used for confidence intervals is based on sample proportion P hat. Again, in our hypothesis test, it's based off of the null hypothesis, not the P hat. That's why it's an approximate. All right. So there is a difference why it's not perfect because of when you look at how we calculate the bottom of the test statistic, we're using the null hypothesis amount in the test statistic, whereas a confidence uses the sample value in the standard error part. On the AP exam, it is acceptable to use a confidence interval rather than a test statistic to address a two-sided alternative hypothesis, but you're not allowed to do it with the one-sided. So if your alternative hypothesis P is not equal, or PO, or P is not equal to PO, P sub O. Again, I did it twice. Then you can use a one sample you can do your confidence interval. If you're doing the greater than or less than simples, we're not allowed to do a confidence interval. We can only do it for a two-sided hypothesis test. And we're going to talk about it a little bit more tomorrow and stuff is like, if our null hypothesis is in the range of the confidence interval, how does that relate to rejecting and failing to reject? Okay. So we'll talk about that. Tomorrow we'll have more time. We get to do the difference between two things. So it's just showing the setup of the formulas, which is sort of lengthy because we get to combine. We get to do some combination of stuff. So, but we'll have more time to talk about just looking at is the null value on a two-sided test, is it inside a confidence interval? And then how does that relate to rejecting and failing to reject?